Welcome. I hope now you can actually hear me. Now I see it on my monitor as well. So I arrived on campus. I hope everything is working fine. And welcome to the first wheel class of Chem 1A. I got a lot of emails from you over the weekend. Thank you so much for writing. I replied to about half of them. The other half of them, I rather wrote an announcement because they were the same kind of emails which I got from different people. And so I hope that many things are sorted out at the moment. So, with regards to the response, that should have all worked fine by now. Several of you didn't see in your gradebook a response that I was telling you of the C in the gradebook. That was essentially my fault because I didn't start the software quickly enough to actually record your responses. So they came in before I started it, but they were there. And because everything from Friday doesn't really count real points, we don't need to worry about that. I think going forward it will work. A very frequent problem with uploading images was that you used an iPhone and had live images on, and then it uploads a file which I can't read. Make sure that live images is switched off on your iPhone if you use an iPhone, and then it will automatically upload the JPEG image. Then homework started, the smart work homework started, and I think we are right now at homework number 4. So on Saturday and on Sunday and on Friday, there was each an homework. Don't panic if you missed them. There will be 50 or 52 or 53 or somewhere thereabouts homeworks, and only the 40 best which you submit count. So you have still the opportunity to get full score. I always leave them open for only about 12 to 18 hours or so, because otherwise I'm afraid that the answer set is being distributed, and then people later in the day have an advantage above people earlier in the day, and that's not how it's meant to be. Okay, after class today, uh, after class today, we will share with you the homework set for the week. That hasn't been done quite yet, but I hope I got the technology for that working as well. That share will come from one of the TAs, Michelle Wirch. She is the person who's in charge of grading it this week. And then starting tomorrow, there will be your discussion groups. In your discussion groups, you will do it on Zoom. The Zoom links for that are or will be posted on iLearn for your discussion groups. And it is really important that for the discussion group, you sign into Zoom with your UCR ID and don't use any personal ID for Zoom, because that is that will not work. Because during the discussion group, we'll break that out into rooms in Zoom, and that goes by email address. And so you need to be signed in with your UCR email address. Um, Also, please do look in your iLearn gradebook. You can find there in which discussion group you're in. You should know that anyway. But you can also find there whether you are part of the first half or the second half of this discussion group. We cut them up into two 25-minute sessions, one starting on the top of the hour and one starting later in the so that you have an even better opportunity to interact with the TA and with each other, so that it's all a little bit smaller groups. And I hope that will work well for you. So if you find that you are in group B and you start at half past the hour, then you only need to show up to your discussion group in Zoom at half past the hour and not earlier. So then lastly, we got a lot of questions how we take attendance during class. There's not directly taking attendance during class, but there's certainly that we'll have some interactive opportunities during the class, and they give you points for the class. And so if you aren't here, then you won't be able to participate in them. And in that sense, it is relevant. Okay. I hope that is fine. I got a question right now. No discussion groups today. Discussion groups are whenever the discussion groups are scheduled. And I thought they were all scheduled for tomorrow, but that might be wrong about that. Good. Then let's see that we get to the book. Let me find my cursor over here. And then get to PowerPoint. Very good. Here we are. I'd like to start with chapter 2 of the book and not with chapter 1 because chapter 1 is very much a recap what you certainly learned in high school at some point in time. I'm going to use that recap a little bit later on in the class where necessary, where we're really using it. But I'd like to really get started off with chemistry or the foundation of that. And with that, I'd like to go back in time because this week is about atoms. We are going to work about molecules and worry about them maybe Wednesday of next week or so, maybe already on Monday, we'll see. But this week would really only be about atoms. Now, I'm sure you all know from probably kindergarten age and PBS shows at the time that there are atoms and that matter consists of atoms. But that is something which is not self-evident, really, at least not to our direct senses. And for the longest time, people weren't really aware of it. In old Greek times, almost 3,000 years ago, people wondered already whether matter might consist of atoms, and they had good ideas about it. But it was certainly not something which at that time people universally agreed about, that matter consists of atoms. Maybe of elements, but those elements might be earth, wind, and fire, things like that. So there were many different theories at the time. And so let us then go fast forward a little bit to 1870 or so. Pretty exactly 150 years ago. Because in that year, something important happened, and that is that a new faculty was hired at a place in St. Petersburg in Russia. And the institution was the St. Petersburg Technological Institute, at least in the translation of the Russian word into English. And the guy who was just hired there as a faculty was Dmitry Mendeleev. And Mr. Mendeleev had then to teach chemistry, which in a technical institute was something new to be taught. There was alchemy certainly in before, and chemistry just from a medicinal point of view had been there for a long time. But really systematic chemistry hadn't been developed yet. And he thought, also chemistry started to have first successes. For instance, aniline was synthesized, the blue color in blue jeans, and so there was the first industrial processes starting new things which otherwise were not available from nature. So chemistry started to become important at that time, and so he wondered how can he teach his students chemistry in a systematic way and not really just teach alchemy. That's how he looked, and he wondered, maybe I should make a list of all the elements and then make a systematic list of that for my new introductory chemistry class, which will be my first class teaching at this institution. And so he came up with a list, and that was his attempt of making chemistry systematic. And it turned out it was the first periodic table ever. Which he published then in Russian in 1871. This is a German translation of it from about the same time. But what you can see here is that he already figured out there are elements like lithium and sodium and hydrogen and potassium and cesium and rubidium and so on, and they kind of are underneath each other. And so everything in a group over here, German word for group, is belonging to each other. And then there are also rows where they all had the same mass. And that was a really great invention at the time. That is certainly the foundation for everything what we call a periodic table. Because it recognized that atoms are in some way are systematically oriented, or elements are some way systematic, that we can find classes, groups of elements which share properties, and that they are kind of repeating. If I'm looking at the list of the masses here, hydrogen has a mass of 1, and noble gases he didn't know at the time, so there's no helium here. But then there's lithium, which would have a mass of 7, and then beryllium, he believed 9, and boron 11, carbon 12, nitrogen 14, and so on. So he had molar masses already, but he didn't know what a mole is. He knew that if I want to make water from hydrogen or oxygen, I need 2 aliquots of hydrogen and 1 aliquot of oxygen. And so he knew the relative ratios for them. And from that, he could devise something which was a mass. But he didn't know atoms. At least he didn't know how big an atom is. He just knew that elements are somehow, if I have a chunk of an element on my hand, it's somehow divided into atoms. And then people tried to figure that out. And we are going to talk for the rest of today how people figured out that they're atoms. And because those are ways where even we can see without much of technology that atoms do exist and how big they are and what properties they might have. So I talked about that, and I talked about that as well. So at about the same time, there was a physicist, J.J. Thomson, and he realized that the filament for a light bulb had recently been developed, and so people could now have something really, really hot inside the vacuum tube. And what he then realized is that if he takes his filament from the first light bulbs which were coming about and puts that over here and applies a big voltage over here, then something will come out of that. And I really wanted to show you a video about that, but unfortunately I have codec problems with that and I'll try it again on Wednesday morning, me showing in class. That's an experiment I usually run in front of the class, but obviously I can't do that online here. Of playing around with electrons, because he then saw that there's something coming out and that leaves a green streak in this vacuum over here. And he found that if he puts a magnet next to this green streak, a magnet with south and north pole over here, a magnet, then this green streak over here would be moved up or would be moved down. And he found that if he puts an electrical electrodes, so charges things up very much here positive and very much here negative. At the time, he was probably using a rubber stick and a cat fur or something like that, and getting lots of static electricity, and then putting one in the bottom and the other in the top. Outside his tube, then the streak of electrons which comes out of here would go up or would go down. They would respond to charge. And so he realized there are charged particles which come out of a filament which is glowing really, really hot in vacuum. And with these experiments of magnets and with the experiments of electrically charged plates, he could determine that those particles were negatively charged and not positively charged. So then he knew there are negatively charged particles come out of here. And then he measured by how much they are deflected over here, the particles, and what magnetic field would deflect them. And out of that, he could figure out what is the ratio of the mass of those particles to the charge of those particles. And it became evident that the mass of those particles is really, really small, or that the charge is really, really big, one of the two, because the mass over charge ratio, if you divide mass by charge, then the thing was really small. And that was very astonishing to him because people at the time didn't know whether elements would be positive, negative, how does they consist of. And what we just saw was, of course, the principle how a cathode ray tube TV worked, where you have the same filament and then the same voltage, and then here again the electric fields to deflect the beam to make the image. Now, what Thomson then thought, good British guy, it's like a plum pudding. Pudding where I have positive charge kind of everywhere, and then there are particles in that background of positive charge, and they are the electrons, and they are negatively charged. So he thought that an atom, the smallest part which still makes up an element, somehow consists of this way, a diffusely distributed positive charge, a charge which he could not get out of his electrode over here, which couldn't go out here as a beam, and then those negatively charged particles which he could extract with his electron tube, which are really light. And so the background is where the mass is, and these ones are really, really small and light particles. And he called them electrons. Reason for electrons, electricity, the whole word comes from the Latin word for amber, electron, and that is because you can get a lot of static electricity with amber. And so people thought, oh, that's initially at least they thought that's a property of amber, and so they gave electricity the name, the Latin name of amber, electron. So the beam from the electron tube was deflected, so somehow there need to be negatively charged particles, and all those negatively charged particles are the same. It was a well-defined beam that he saw. It was not particles going every which way. And those particles, the negatively charged particles, were the same, no matter whether his filament was made out of gold or platinum or whatever different material he used for his filament. So it was independent of the element, which was really astonishing at the time that they were so similar in a way. And he then determined the mass over charge ratio. So the next person who became really important in this was Robert Millikan, another 20 years or so later. And Robert Millikan, he was a faculty at the University of Chicago, I believe, and he set up an apparatus which I hope I can show you a movie about. Let's see that my movies work.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Okay, so now Millikan figured out what is the charge of the electron. And as Thomson already discovered what is the ratio of the mass to the charge, one could easily calculate the mass of the electron as well. And that mass of the electron became turned out to be a very, very small mass. So much less massive than the elements themselves. So there needed to be mass somewhere else. So in Thomson's plum pudding model over there, there needed to be a lot of positive background charge, positive background mass, positively charged background mass surrounding it. That was the next thing that was found. And you probably recognized how simple an experiment it was, what we just looked at. It was really just some oil spray, some mist of oil, where the mist droplets are falling down, and then between those two plates, and the drops are charged by the X-rays. And once they are charged, you can manipulate them with an electrical field and you can suspend them. You just look like a looking glass, a little bit like a microscope in there. And you can measure something as fundamental as what is the charge on an electron, which is, I think, quite amazing. Um, okay. Um, so, what are the particles for the positive charge? Then people wanted to figure out. And somebody really important in this regard is Henri Becquerel. Henri Becquerel was one of the first chemists who concerned himself with radioactivity. And his great discovery, if you wish, is that he realized that that radioactivity are individual decay events, often many of them, but countable. It's not like a continuous thing that radioactive radiation is emitted, but it's really one event. A burst of radioactivity comes out, another event, another burst of radioactivity comes out, and so on and so forth. That you can separate radioactivity in individual events. And So he could also, together with Rutherford and several other people, classify what kind of radioactive events they are. And I think I might have again a short
In
video
1909, Robert Millikan, working at the
video
University of
about.
Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole.
The British scientist Ernest Rutherford was one of the first to show that radioactivity could consist of three distinct types of radiation. The three types differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into three components. One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays. Other experiments showed later that the beta rays are actually high-speed electrons. The alpha particles proved to be helium nuclei. The gamma rays are high-energy photons, analogous to X-rays.
Okay, so Becquerel first saying they're individual events, and then later on Rutherford determining that if you have a radioactive source, there can be three, in reality, there are actually four types of particles coming out. So that which are called beta, alpha, and gamma in in this order, in the order that they had in the movie a moment ago. And one of them was positive. So Rutherford then thought, if I have positive rays which come out from somewhere, from which I can shoot out of my radioactive sample through an aperture onto um, whatever I want to study, can I use that in order to figure out where the other positive charge is? And so so the idea was a little bit like if you want to figure out where in a drywall all the studs or so are, let's use a shotgun and shoot through the drywall over here, and wherever uh, the shot will bounce back and not penetrate through the drywall, there probably was a stud. And so that was the approach which Rutherford wanted to take to figure out where and what the properties of this plum pudding positive charge in the Thomson model would be. And so then he ran his experiment, and he again was very much astonished by what came out because it was not what he expected at all.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
And that was something really astonishing because it said, going back to this image over here, that there are actually studs, there are actually hard parts in the matter which can scatter the alpha particle back, where the alpha particle can bounce against and return. And then there is lots of empty space where the alpha particle can go all the way through. And if you thought in before of the plum pudding model, where the charge is all distributed over here, just everywhere, that wouldn't work. There was, but if you have the positive charge everywhere uniformly distributed, there would be nothing to bounce against for the alpha particles. The electrons are way too light. They couldn't be it either because the alpha particles are way heavier. They wouldn't bounce back from just hitting something as light as an electron. So, so what Rutherford then found, much to his astonishment, because he wanted to prove that Thomson is right, was that this plum pudding model doesn't work. That there are somewhere hard portions in this atom. Now, before I go on, what this is, I'd like you to sketch what we just saw, what Rutherford's experiment was. So you have 3 minutes time, and this bar will show it to you. And I hope in the next 3 minutes you're going to upload me in the website your sketch of Rutherford's experiment as we saw that in the movie ago. Okay, you can see the time is kind of running, and I might extend it a little bit for the time I spent talking, but I hope you'll upload soon. And don't forget, if you take the photo on an iPhone, don't have live image on. Don't forget to label it. Doesn't need to be long labels, just a word here, there, source, things like that. Okay, so last extension. Okay, when this bar is over, I'm going to continue it. I hope you'll have all uploaded your images. Okay, let's move on. The other question which I had for you still is, remember what we had in the Rutherford experiment in a moment ago? What was the result he found? And the other one of those ones which I'm showing over here is the one he expected. But which one of those two is the one which he found? Please clicker that in using the site, using A or B. And please don't click it in actually, because I haven't started it. I need to get better about that as well. So let me. Now it started, so click it in now, please. I was asked, can I repeat the question? Which of those results is the one which she actually found? Was it A or was it B? Were the particles scattered back like it's shown in B, or were the particles scattered back like shown in A? And if you responded twice to that question, that is not a problem at all. So, okay, then I'll stop that now, and then we should go on. Okay, so what he found back that was that the particles were scattered backwards as well, that they were actually hitting something hard in the atoms, and that they were not all deflected just a little bit, what he expected, but rather there was something hard somewhere in the middle of the atom which made things bounce back. And as a consequence, he realized that there need to be some hard nuclei in the atom. So that was something like the sketch which I hope to get. I mean, it's way more elaborate than you can do it in 3 minutes, but something of that sort was a sketch of an experiment. So then he evaluated how many of the particles were actually going all the way through, straight, without hitting anything, and how many of the particles were deflected to the side in total. And from that, he could figure out how big are those hard parts where the alpha particles where the radiation was scattered from. And he found that is really, really small. So if you were in a soccer stadium, it would be about a soccer ball in size compared to the whole stadium. So the nucleus would where the alpha particles were scattered were like the soccer ball there, and then the whole atom would be the size of the stadium. There is something really small inside the atom which is really, really massive, and that is where the scattering happened. Okay, so Mendeleev says there are systematics in chemistry, there are systematics by the elements. J.J. Thomson said, okay, we have electrons in any element, no matter which element we are taking, is always the same electron which comes out. The electron is really light. It's about 1,000th or 10,000th or even only 100,000th of the nucleus of an atom in mass. And it is negatively charged. And then Rutherford found there is something hard and heavy and positively charged in the center of the atom. Now, the mass was not in the electrons. If they are just 1,000th or 1/10,000th or so of the mass of the nucleus, then that is completely irrelevant, their mass. But then is the question, why are the masses going as they are over here? Hydrogen having a mass 1, and then lithium 7, and then carbon having here 12 or so. That makes no sense in a way. The masses, they do not go like hydrogen has 1 mass, and then helium, which you didn't know, has twice the mass, and then lithium has 3 times the mass of hydrogen, and beryllium 4 times, and then boron 5 times. It wasn't like that. So even though it was found that the hydrogen and then helium and lithium and so on had each one electron, one more positive charge in the nucleus, their masses didn't scale by how many more positive charges they have. So in the nucleus, there need to be something which has the mass, and there needs to be something which has the charge. And maybe the particle which has a charge also has mass, but there needs to be also something else which doesn't have charge, but still adds to the mass. And so then an even more complicated picture emerged. We have the picture where we have negatively charged electrons. They take up the whole space. They can be anywhere, really. People didn't figure out where they are. They can be anywhere. And somewhere, presumably in the middle, but somewhere at least, there needs to be a small hard object, and that small hard object needs to have the charges in there and something else which gives additional mass as it's needed. And so the particles which have the positive charge there were called protons, and the particles which don't have any charge, they were called neutrons. So we have now an even more complex understanding that we are not only having elements, but the elements consist of atoms, and the atoms have electrons in them, which are the same for every element. Maybe how many there are is different, but it's the same kind of electrons. And then there is a nucleus in there, and the nucleus has really the mass of it, and the nucleus needs to consist of positively charged particles which have a certain mass, and neutral particles which also have a certain mass. And it turns out that the mass is fairly similar. The neutron is a little bit heavier than the proton, but only by a very small fraction, by less than 1%. So they are pretty much the same in mass. So that is what was found then. Okay, we have that. Now for each element, we need to have the same amount of positive charge. That is really what defines an element. So what defines an element what defines where in this periodic table by Mendeleev it is, whether it's here or there, that is defined by the number of positive charges in the nucleus. But then for each element, there might be different number of neutrons in the nucleus, and they change something about the element, namely its mass, but they don't change its chemical properties. And so it still says chlorine, for instance. So over here we have chlorine, and there are 3 isotopes of chlorine, 3 different nuclides of chlorine, one which has a mass of 36, which has 36 nuclear particles, either protons or neutrons, and one which has 35, 1 neutron less, and one which has 37, 1 neutron more. Number of protons is the same for each of these elements. So the protons give the positive charge and define whether the nucleus belongs to this kind of element or is another kind of element. The neutrons give the mass, and there can be different number of neutrons in a nucleus, and you still get the same element. You get just elements with somewhat different atoms of the element with somewhat different properties. And then there are the electrons, which are surrounding the nucleus, and they are far, far out, whizzing about, moving around, being much, much lighter. And typically elements are neutral. And so you have the same number of electrons in surrounding the nucleus as you have protons in the nucleus. Okay. So the important word to find here is isotope. The word isotope over here. An isotope, iso means the same, tope comes from topos, the place. So it is at the same place in the periodic table because it's the same element. Chlorine is always at the position of chlorine in the periodic table. But it can have different masses depending on which isotope it is. It has different number of neutrons, but the number of protons is the same. So then we have one more of those questions where I would like to get a response from you. And if you look at the periodic table, and you can use any one you like, then you will see that are there more protons than neutrons in the nucleus, or are there more neutrons than protons in the nucleus? Typically, there are exceptions, but typically, if you look in the periodic table, in the nucleus of which species do you find more? So you have a moment to submit your question now. Feel free to submit it twice if you think the first one wasn't accepted. Okay, and then let's go on. And yeah, that's what I thought. We are done. So at this point, we've looked at how is an atom being set up. I will hopefully be able to show you the Thomson electron tube experiment at the beginning of next class. I hope I get the videos codecs working for me as they should. Then the next time you meet us will be the discussion groups, for most of you at least tomorrow. And you're going to be shared a document for your homework in the next hour or so, I hope, if everything works in technology. You will work on your homework in groups of somewhere between 1 and 4 students. And who is your group partner? You can see by who your document which you're receiving shared from Michelle, TA Michelle Rich, who the other partners in the sharing are, and then you can email them. And also you're going to meet each other during the discussion groups for most of you tomorrow. That is how it further goes on. And we will see that we grade your clickers from today, and that we grade the images, and that we find the best ways of uploading them. And I hope we'll have that done by Wednesday. So with that, thanks so much for tuning in. Bye now.